questions about anything we've done? So, 2, 4, 6, 8. I'm short a few people, but I want to cover central moment ideas. I mentioned this one other time. This becomes very useful, especially in things we're going to do in chapter 3. So the central moments, I'll just go through this kind of basically. You know, anytime we talk about the expected value of anything, doesn't matter what this function is, what you're really doing is taking an integral over all possible values, or a summation. Now we'll talk about delta functions a little bit today. But when you do this, you're always going to have whatever it is you want an estimate or the mean of. And then it's always the density function. And that's just the general idea. I think everybody knows this. If this was x, it would be the mean. If it was x squared, then it would be the mean squared value. If it was the quantity x minus the mean quantity squared, that would be the variance. Do you all follow me in this class? And it goes on and on. You can extrapolate this to anything. But one of the things that you have to be aware of are something called central moments. So when you take the expected value of x, doesn't matter what the variable is, I'm using x, minus the mean of that. And with the central moment, what that means is it's going to be to the nth power. Do you all follow me on this? And it's usually rendered or usually shown as x minus x bar to the nth power. Now, x minus n bar to the nth power with a bar over it. The bar over it means it's the mean value of whatever's under the bar. That's all that means. I think you're all together on this, right? Now, when you have the central moments, when n is odd, it's always 0. This is n odd. And that's true. And by the way, this is true for Gaussian and other distributions as well, but specifically stay on Gaussian. Are you with me on this class? For Gaussian stuff, this is where it's so valuable, because higher order moments with Gaussian distributions they become difficult. If, like after fourth or third order even, fourth order, you know, the mean squared value is non-zero almost always. It has to be actually. But the central moment, or the actual x minus x bar, the expected value of that to the third power, fifth power, is always 0, and it's because of arguments of symmetry. So it's always 0 here, and I put it this way, I really should put the bar over here. And it will be 0 for n odd. And then whenever you have x minus x bar, and this is the expected value of the nth moment, if it's even, it's 1 times 3 times n minus 1 sigma to the n, and this is n even. Does anybody remember me mentioning this at all? We talked about this just second order. Remember, the variance was equal to the mean squared value minus the mean value squared. Do you all remember that? I mean, that's critical, and you have to know that one. But this is really important. Now I want to talk a little bit about this, because here's where there's some confusion the way it's rendered. 1 times 3, so these are odd values, right? If the value was 3 here, it would just be 1 times sigma to the n. Right? What this means, if like n is 5, you'd have 1 times 3, and then you would have 5 minus 1 is 4. So 1 times 3 times 4, sigma to the 5th power. Do you follow me on this, class? That would be for n even. And the formula is in the book. I wish I had the page number. But this is something you're going to need to be aware of and use. I'm trying to be clear about this. Now, when you do central moments like this is easy to calculate. Right? What isn't easy to calculate is, like, if we take this and, I'm sorry, this I should say for n equals 4. So It would be 1 times 3, and then 4 minus 1 is 3, sigma to the 4th power. It's easier to do this and find the mean value and then work backwards. And let me just expand on this. Let's assume n equals 3. If n equal, I mean not 3, n equal 4, then you're going to have x minus x bar to the 4th power here, and that would be equal to 1 times 3, and then it's going to be times 3 times sigma to the 4th here. And if you expanded this, you would have x squared minus 2x x bar plus x bar squared times x squared minus 2x x bar plus, or I'm sorry, yeah, plus x bar quantity squared. And you have to multiply all those out. And y'all see what I'm doing here. I'm just taking this, and it would be the expected value of all that. You all with me, class? I'm just squaring this stuff right here. Now, I don't expect you to spend time doing that. And so in the higher order moments, I'll give you the general form of this. This is for 4th order, and I've done all of these things before. Let me see what I'm trying to give you a page number for this, because at least I want you to appreciate this stuff. And you have, so you know when it comes up where to get it. This is on page 72. And what it'll boil down to, when you're all done with all the, when you do all this, I mean, this is going to be a straightforward operation, but it's a little long. This is going to be x to the 4th, following, and you have this times this. Then you're going to have minus 2x to the 3rd, minus 2x squared, x bar squared, and then it's going to be minus 2x, x bar, this would be minus 2, I have this times this is x to the 4th, this times this is going to be minus 2x cubed x bar, this times this is x squared x bar. Then you would have to do that for this one and this one. You're going to get a lot of terms. I think you're going to get 9 minus 2, so you're going to get 7 terms, and then you start combining. You all follow me on this? It takes a while to do that. It's irritating. Well, irritating to me, because after all is said and done, this whole thing will break down to, and if what I'm really getting at is I'm trying to get x to the 4th out of this, because we will be using, in the next chapter, we're going to be using the 4th moment, not the 4th central moment, but the 4th moment. You follow me? We're going to use this for stuff to find the variance of the variance, and you'll see some of this stuff gets a little crazy quick. So this is going to be 3 sigma to the 4th plus 6 sigma squared, and then it's going to be the mean value squared plus the mean value to the 4th power. Put down, this is on page 40, or on page 72, just so you have a reference for it. I want to make sure you have that. Anyway, the whole idea about this is this general form for n even will allow you to actually, if you expand this thing, to calculate the value of the higher order moment. In this case, if it's 4, it would be x to the 4th. It gets you there. But this is the formula you would actually kind of lean back on. You all follow me? Third order moments aren't that bad. And there are forms for that, and I'll give you that one too. And I think that one's probably, because the central moment, if n is 3, the central moment is 0. So if it's 0 on that side, you just expand it, and then solve for x cubed. I'm trying to figure out. I'm looking for it. I'm not not seeing it. Anyway, I'm just making mention of that. Be aware of this, and when this actually comes up in the next chapter, I'll make sure I underscore these things and what you need to know. I mean, that I'm not going to give you. I think I'll give you this one on a quiz or test, because frankly, it takes too much time to expand this. It does. The next thing I'm going to talk about, the central limit theorem. This is sort of, it's something that's important to at least have an understanding of, because later on you're going to see, depending on which way you go in your career path, it becomes useful for any kind of large-scale operations where you're trying to estimate the number of, you might say, defects or anything like that. And I'll tell you, the central limit theorem really is something where he does it in his book is, he doesn't really show how useful it is to operations. He gives you the straight math on this one. So it really says if you have a new variable y and it's equal to the summation from I equals 1 to n of 1 over the square root of n, and now you're going to have x of I minus the mean of m. So this is something where now you're creating a variable from other variables, and I didn't say this, but if you have a summation of a whole bunch of random variables, call it x. Call a random variable x, and all these random processes have a mean of m. With me on this? Now you can assume Gaussian for that, but you don't have to. You got random processes, and it could be anything. It's got say, the errors in a VLSI processing. Right? So you got something that's creating chips, and you know statistically the errors have a Gaussian distribution with a certain mean value. And that's for process A. Then there's process B, identical to process A. Then process C, and all this stuff. Basically, you've got a whole bunch of processes that have the same, I guess, the same basic structure and character. So everything is statistically the same. Now you want a variable where you're going to calculate something about the average value or the probability of things of all of them added up. And this is in processing. There's a lot more detail to this, but this is actually done. You want to find out an estimate of the statistical nature of the process. If you add all those up, you get a new random variable. And what you find is this random variable, if you subtract the mean from these, will have zero mean. And remember, the mean is something that you get by repeating the process many, many times, and this is how they actually come up with these distributions. And then they look at the mean value of the process over a large period of time, and they use that. But this will have a zero mean, and it will have a Gaussian distribution. Now, I mentioned the process for the central limit theorem. I said assume they're Gaussian, even if they're not Gaussian. It doesn't matter what the distribution is. If they have the same mean, and it doesn't matter if it's a constant, f of x is constant, it doesn't matter what the distribution is, as long as the distribution is the same on all of them. In the end, you'll get a variable y, if you have this summation right here, that will have a zero mean and it will have a Gaussian nature, even if the statistical processes we're talking about don't. Now that's important later. It'll become important, not in this class so much, but in upper level courses if you get into any kind of process engineering or information theory. And I say that, I'm not absolutely sure with information theory, but I think it's true. Central limit theorem is very famous, but it's not useful right here and now. It's in the future. And you'll just have to appreciate this. You realize the nice thing about Gaussian, I think everybody knows, is it's symmetric about the mean. It's not only that, it's very easy to calculate statistical information about errors, the probability of a certain level of error, and that translates a lot of times into an expected value for what, actually the monetary return on what you're doing. So this is kind of downstream from what I'm talking about now. By the way, how many know what an actuarian is? Anybody? You do? These are people that are gifted, really, they're highly trained in mathematics, and they're used by insurance companies, banks, to take a look at what the loan, or what charge they should have on a loan or anything, and how to actually assign risk rates, interest rates, all this, so they make a certain profit. And this, it gets really complicated, but actuarians are very, very valuable. They're highly paid because they understand the statistical nature of whatever they are dealing with, primarily the monetary system that they have to deal with. I'm not sure how long it takes. You have to go through all these tests to become a license. I mean, to have it become an actuarian that's used by insurance companies and banks and stuff like this. But companies like Google and Intel and stuff, they employ them too because they want to make sure they make a profit. And they have all the information, statistical information about the processes and everything else, and they work it into equations. Now, I'm just saying that because it's mentioned in the book, you should at least be aware of the central limit theorem. The takeaway from this is, no matter what the processes are, if they're identical and have the same mean, then you can create a variable. It's just a summation of all these processes, and yet we'll have a Gaussian, if it's a lot of processes, I should say it has to be a large number of processes, that will have a Gaussian distribution. That's all, with zero mean, for now. Next problem I want to do, and this is something you did for homework, is 2-6.4, but I want to mention a few things about this. We did that problem. Hopefully everybody. Remember? This is the one with the marbles. You guys remember this? You do? How many did it? I'm curious. 1, 2. A lot of you didn't do that one? It's a straightforward problem. It's a pretty good problem. For that one, it says 2-6.4. It's got a standard deviation of velocity of 4, and the units would be feet per second, which means variance is 16. And it's saying that these marbles are in a two-dimensional plane, and that's the velocity. That's if they have a Rayleigh distribution. And the first thing they ask is this, and this is a good one. So I'm going to tell you, this kind of a question appears, and a lot of people don't know what to do with it. So the first question asks, what is the most probable value? So now, and this is an Rayleigh distribution. So first, you have to take a look at what the Rayleigh distribution looks like. So f of r is equal to r over sigma squared. And by the way, that is the sigma associated with the x and y Gaussian distributions. You with me for the velocity of x and y? It's important to know that. This is r, and it's times exp minus r squared over 2 sigma squared. You need to know that distribution. I mean, you have to. And you have to know what I might as well put it here. You have to know this one. F bar of r equals 1 minus exp to the minus r squared over 2 sigma squared. And this just says the probability of the event, the random variable, whatever it is in this case, r, greater than 0, less than, I should say small r, capital R. Really, it's the probability the event is equal to or less than r, from 0 to r. That's basically what it's saying. So it looks like this. At 0, it's 0, and it does this. Kind of has a Gaussian tail to it. So they're asking the most probable value here. This is r. How do you get that?
It's just the mean.
Say again?
It's just the mean.
No, it isn't.
Standard deviation.
Yeah, but how do you get it? is what I'm getting at. There's a process that everyone knows. How do you find a maximum of any function? Take the derivative and set it equal to 0 and solve for the value of r for that. You all with me on this, class? How many understand? I mean, because, look, when you get to Maxwell-Boltzmann or other distributions, you don't know what it is until you do the derivative and set it equal to 0. Follow me? You have to do that. And by the way, when you set it equal to 0, there might be multiple zeros, and you have to evaluate each of those values in the function to see which one is the maximum. So for this one, if we take this function right here and take the derivative of fr of r with respect to r, and take a look at that, I can factor out the 1 over sigma squared, and I will. And then if I take the derivative of this, take the derivative of r, I get 1, so then I get this e xp to the minus r squared over 2 sigma squared plus, and then I leave r alone, and I take the derivative of this thing. That means it's going to be minus 2r over 2 sigma squared. It's going to be times e xp to the minus r squared over 2 sigma squared. And that whole thing is set equal to 0 to find the maximum. How many agree with that? With me? All right. Now, it's easier for me to do this on the board by erasing things, but everybody should at least be able to do this without any kind of angst, without any problem. If I look at this, since it's equal to 0, I'll get rid of this whole thing. I can get rid of the sigma squared. Do you agree with that? It's 1 over sigma squared. Multiply both sides by sigma squared. 0 times sigma squared, still 0, get rid of it, right? Next thing is you see the exponential e to the minus r squared over 2 sigma squared appears in these two terms. If I just divide it out and divide the 0 by that, I get rid of this 2. This becomes a 1. And that becomes a 1. So now I have that. Do you agree with me? Just making sure. Believe it or not, I asked this thing, and it's silly, something like this, and I'll get wrong answers. And I don't know why, but I'm making sure everybody sees this. Now, the next thing I have, this is a minus here, right? But you'll notice the 2 go away. And it's that. You agree? So now I have r squared equals sigma squared, or r equals sigma. And that is the sigma associated, that is the value, that is the most probable value of r. Y'all with me on this? Somebody knew that. Did you say that? One of the two of you said it, Michael. Yeah. That is the right answer. So here, the most probable value is sigma. What's the mean value?
0.
No. Think about this. It exists from 0 to infinity. It can't be 0. Do you remember the mean value for the Gaussian, for the Rayleigh distribution, guys? Well, we need to know this. What is that? It was equal to the square root of pi over 2 times sigma. Y'all remember this? How many do? All right. And what was the actual mean squared value? Wasn't it 2 sigma squared? How many remember that? Isn't that right? You're looking at me funny like I'm wrong.
Well, I'm just thinking about it.
I'm looking at this. Yeah, that's the value. Now, the value, I want to mention this. This gets a little confusing, so please pay attention to it. This value of sigma is the sigma associated with the two-dimensional distributions that this Rayleigh's comes from. They have to be symmetric. They have to have 0 mean. Everybody with me on this, class? So that sigma would be the Gaussian sigma. Now, there is a standard, there's this right here, that's the mean value for the Rayleigh distribution in R, not the Gaussian distribution. With me? Gaussians have zero mean. This is the mean squared value of the Rayleigh distribution, but the mean squared value of the Gaussian distribution, well, the variance of the Gaussian distribution would be sigma x squared, right? You'd need the mean value is zero. So in fact, because the mean value is zero for the Gaussian distributions, the mean squared value is the variance. Follow me on this, class? So effectively, that means the mean squared value for that is twice the mean squared value for the Gaussian. Just making sure I say this. Now, if I ask for the variance of the Rayleigh distribution, we've got the mean value, but what would the variance of the Rayleigh distribution be? And I'm going to write VAR here. Just think about what you got in your toolkit. What's the variance of a Gaussian? Sigma squared, what is it? Do you remember for a Gaussian it was equal to what? X squared bar minus X bar quantity squared, right? Well, here it would be R squared bar minus R bar squared. Got that? Now that's for the Rayleigh, not for the Gaussians that the Rayleigh is based on. For this one, this is one of those things you can just take these and get. So you've got 2 sigma x squared, and then you're going to take minus, and when you square it, it's going to be pi over 2 times sigma squared, sigma x squared. And you can get it that way. In the book, I think he has it like 0.6234, something like that, sigma squared. Do you all remember that? How many remember that part of it in the PDF? Nobody? You didn't see it? It's there, and it's useful to know that. But you can always get it from that. That's the point I'm making right here is if, for whatever reason, you don't remember, go right here and you can get it. With me on this? Okay. Now, I mean, when you have a problem, here's the way it could be constructed, just to give you some insight into the way things might come at you. Suppose I gave you the variance on the Rayleigh. In other words, I give you this information. With me? I didn't give you the Gaussian. And I give you the mean squared value of the Rayleigh. Follow me? If you have those two things, you can get sigma x squared, right? For the actual Gaussian distributions the Rayleigh's made of. And you know that if you're talking about Rayleigh, the Gaussian distributions it's based on have zero mean. So once you have that, now you have all the information you need to use this to find the probability of anything in the Rayleigh distribution space. Yes, sir?
Are those the sigma sub v's at the front? Are they
Pardon?
different from the sigma v's? Are they different from the sigma x?
No,
squared?
sigma v, that's the velocity distribution for sigma x, or for v of x or v of y. If you read the problem, you have I can give you 6.4 right here, and you can read it. But I'm trying to bring out some points with the Rayleigh that can confuse people if they don't see it. One is the Rayleigh's distribution variance is different than the Gaussian distribution variance, and the mean is different. Those are the two things that are essential to notice. Now, how they relate is what I'm showing you here.
But those sigmas are the same as the sigmas on the
Yeah, they're based on the Gaussian, all right? So, because he says in 6, do you have it with you?
Yeah.
All right, can you just read that real quick, and we're getting back to this problem, but I had to.
Marbles rolling on a flat surface have components of velocity in orthogonal directions that are independent, Gaussian random variables with zero mean and a standard deviation of 4 feet per second.
They have Gaussian distributions in x and y. Say that again? Sorry.
They have components of velocity in orthogonal directions that are independent Gaussian
All right.
random variables.
That's where sigma x that he gives you is going to be a Gaussian sigma. It's associated with the Gaussian distribution for v of x and v of y. He doesn't, he says orthogonal, but really, just think vx, vy, they're orthogonal. Now, that means, now we actually can use this statistical package. So, or what I show you here is the distribution for the Rayleigh. The first question was, what is the most probable value? And that is R is equal to sigma, which is not the mean. That's my point on this one. With me on this, class? The most probable means the value where the probability density function for the Rayleigh is maximum. And whoever said mean when we start, I asked that question, that is what you would think, because in a Gaussian distribution, the mean is the largest value, but it's not for the Rayleigh. With me on this, class? Okay, now what is the next part?
Find the mean value of the speed.
Mean value of R, or of the magnitude of velocity. So here, I'm just going to put this up here. He's saying that V magnitude is equal to the square root of Vx squared plus Vy squared. Since Vx and Vy have Gaussian distributions, this is the same form of the actual formula that the Rayleigh is based on. The Rayleigh distribution is based on the fact that R is equal to, I'm using x squared plus y squared. There are any two orthogonal coordinates in a 2D plane. Now, both x and y have zero mean, and they are assumed to have the same sigma, same variance or standard deviation. And the effect of that will be, if you go through the mathematics on this, is when you get the statistical information here, you in fact get the Rayleigh distribution. So part B was they want the probability the velocity is.
Part B is find the mean value of the speed.
All right, now the mean value of the speed is just the mean value of the Rayleigh distribution that gives the statistical information about the speed. So the mean value of the velocity, this is effectively R bar. So I can call it magnitude of V bar. Are you with me? Because that V magnitude is the same thing as the R in the Rayleigh distribution, effectively. How many see this, by the way? Can you see it? All right, what is it going to be? That was the default formula. And it was what? Square root of pi over 2, right, times sigma of the x or y, the Vx or the Vy. With me, class? And I don't know what that is, but it's something larger than 1, because square root of pi over 2 is larger than 1, right? And you can get that. Can you give me what that value is, anyone? Sigma x is 4.
5.013.
And I believe that's the right answer. I mean, I gave you the problem. I think I gave you the solution, man. Did I give you the solution on one for this?
I think they just posted 2-613.
All right, well, this one is in the solutions manual I posted, I know that. But you all see how to do this? All right, so that's the mean value. What's the next question? Remember, the mean and the actual most likely value are different for Rayleigh. That's the point of this problem. What's the next one?
What's the probability of finding a marble with a speed greater than 10 feet per second?
All right, how do you do that one? Well, we're really looking at this. If this is 4 and this is 10, we're talking about the area under the curve here, right? Do you all agree with that? Okay, think about it. This is what? If you think about this for the velocity, just write it right here so you can see it. That would say my f of v magnitude less than some value, in this case less than, less than anything really, I'll call it A, is equal to 1 minus txp minus a squared over 2 sigma squared. We've got sigma given to us, right? That's being less than that velocity, right? The probability it's greater than that velocity would be 1 minus that. So if I take probability of the magnitude of V being greater than whatever A is, I can put 10, 20, 100, doesn't matter. That's just 1 minus this. 1 minus F of magnitude of V less than A. And the neat thing is, just by looking at this, you know it, it's just EXP to the minus A squared over 2 sigma squared. That A can be anything, so that's the probability of the velocity in this case being greater than A, right? A for this one was 10, right? Okay, so this should be straightforward. It's just going to be EXP to the minus 10 squared over 100 over 2 times 16. And that's going to be simply EXP to the minus 100 over 32. And I don't know what that is, but I did do this. It's the right answer. The solution's one. Anybody?
Yes.
You can see that's very small, 4.4% chance of being greater than that. He's giving you just some insight into when you see something like this with a Rayleigh distribution. Now out here, they call it the tail. Now remember, the standard deviation is 4, right? And the mean value is going to be 4. The most probable value is 4. So here's 4, right? Think about the Gaussian. Remember, if you're 2 standard deviations away, what happens to the value? It's like, it's under 30%. I don't remember the exact, but it's very low. Here, 1 standard deviation from here would be 8, right? If that's 4, it would be 8 in terms of the Gaussian standard deviation. In terms of the Rayleigh standard deviation, it would be 2 sigma, or square root of 2 sigma, which is very close to that value. But we're going to see a value that 4.4% is almost nothing. I mean, it's crashing very quickly. If you went out from 10, if you went out another standard deviation to 14, you'd find this thing is basically 10 to the minus 5, 10 to the minus 6. So it goes down quickly. All right. Is there another part? You with me, class? All right, wanted to do that one. Got a few things. Now we kind of really went through the Gaussian, and if I have a Gaussian distribution with a probability of a certain being greater than a certain, like a third or a fourth or a fifth, and less than a certain value, you know how to do the inverse on that. We've gone through that quite a few times. We'll talk about it for 2 lectures. And the next thing, I'm trying to make sure I cover the material that needs to be covered on this one, in this class. Okay, just going to touch on this. I'm going to tell you, Maxwell-Boltzmann is something, if I ask you questions about the distribution, I would give you this distribution. I won't give you the Rayleigh, but I'll give you this one. For the Maxwell-Boltzmann distribution, it's based on the velocity space in gases. And it actually is very active. So they talk about V being equal to the square root, and this is V magnitude, Vx squared plus Vy squared plus Vz squared. Do y'all remember, you've had basic chemistry and stuff, right? And you've had thermo. Did you have thermo yet? All right. There's one thing that sticks out in my mind. Do you remember there was a energy associated with the molecular energy for single molecules? What, 3/2 kT? Do you remember that? 3/2 kT? Whenever I get this, it's like, I've heard of that somewhere. All right, that's kind of one of the, you know how V equals IR, if you're an electrical engineer, that's like the gospel of circuits. If you don't know that, you're not an electrical engineer. I'm just saying, it doesn't matter. If you don't know that, you're out of here kind of deal. If you're for a job interview and it says you're an electrical engineer. Well, if you go and you're anything, either chemistry or mechanical engineering, and you don't know what 3/2 kT is, they're going to look at you and say, there's the door, goodbye. It's that level of knowledge for basic thermo and chemistry. Anyway, for this, the velocity distribution, I didn't say this actually, but of the magnitude of V, we're assuming something about this. It's assuming that the velocity distribution, and this is actually proven, for the Vx component in molecular movement is Gaussian with zero mean. For the V, unless there's a skew, like an electric field or something that's pushing ions. I had to do all this stuff in plasma chemistry when I was in grad school. I did a bunch of stuff with plasma. My master's work was in plasmas. But anyway, assuming there's no skew caused by an electric field or any kind of a gradient in the pressure, then the velocity distribution for x, y, and z, Vx, Vy, and Vz, will have zero mean, and it will have a Gaussian distribution. And that's based on mathematical statistics too, by the way. It's an absolute, rock solid proof. From that, based on that, now this variable, similar to the Rayleigh if you think about it. Rayleigh only had what? Vx and Vy. And we saw something coming out of that the actual variance of the Rayleigh was 2 sigma squared. Remember that? That was the x, y, and z. So I better put this up here. There's going to be a sigma x that equals a sigma y equals sigma z. And it doesn't matter if I can put velocity in front of this, but it's the x, y, and z standard deviations of whatever we're talking about. In this case, velocity are the same, and there's zero mean. That said, when I look at this, it's going to have a similar form to the Rayleigh, but there's some difference with constants. You're going to get square root of 2 over pi here. That's a weight. Then you're going to get the V, not just V by itself, like with the Rayleigh, it was just R, but it's V squared, and it will be over sigma squared. But the Rayleigh was over sigma squared. Then you're going to have EXP here, and it has the standard just V squared, or magnitude of V squared, over 2 sigma squared. And this is sigma of Vx, Vy, or Vz. So the takeaway from this, the exponential variation is the same as the Gaussian, as the same as the Rayleigh. The difference is in the weight here. Now instead of having R, we have V squared. And remember, for the Gaussian, you had no weight here, no velocity, no kind of a variable there. It was just 1 over the square root of 2 pi times sigma. There's going to be a square root of 2 and a pi, but they're in different locations. Pi is downstairs, but 2 is upstairs. And you get the sigma squared that you see with the actual Rayleigh. So that's the distribution. Now, I'm going to just mention 2 things and move on. The actual value of the mean squared value of the velocity is 3 sigma squared. Remember this, there's zero mean x, y, and z velocities, right? For the Rayleigh, it was 2 sigma squared for the mean squared value. And for this one, it's 3 sigma squared. It's almost like dimensionally, as you get one more orthogonal dimension, it goes up. Now, in truth, there are distributions that get, in physics, they talk about time as a dimension, and it is, and it's worth, and you can't visualize this, is the problem. So if you had a function that is a function of time included in Vx, Vy, and Vz, and this is called Minkowskian space. In electromagnetics, we have things where we basically use time as a variable. And then you would have something where I believe in, I didn't look this up, the mean squared value in Minkowskian space of, it's really not even a velocity, it's sort of a hybrid thing, because velocity, when we think of velocity, we're thinking about the same instant in time. But now we can take a look into the future or back in time where the velocity will be different, if that makes sense then. This gets a little too far into the abstract world. But this would be 4 sigma squared. And that doesn't matter to us. And I better be careful about this. I didn't look this up. So maybe scratch that one. I have to look it up. But there are things where you can extend this into other dimensions. And by the way, in the world of mathematics, there's a book by Spencer and Moon that I have upstairs. I have a PDF of it, if anybody's interested. And it has all the differential equations, the Helmholtz equation, which is basically in electromagnetics, it's the wave equation we talk about. They do the separation of variables in all the coordinate systems, and there are I believe it's 10 separable coordinates. You're used to Cartesian, cylindrical, and spherical. Remember, you did separation of variables, or you're going to in EMAG 2, right? You did it in mathematics. That's how you solve differential equations, or solve things that have, like a variable that's a function of two orthogonal coordinates, right? Or 3. Well, that's Cartesian, cylindrical, spherical. There's proloid, spheroid. There's elliptic, what do they call it? I think it's called elliptical, circular, and there's all these other separable coordinate systems. The proloid spheroid is based on an egg shape. If you think of an egg, you have something where you have a spherical distribution, you stretch one axis, and you get an egg, basically. Think of it that way. Well, those surfaces represent constant, you know how, if you take square root of x squared, y squared, and z squared, you get a radial distance that has to do with the spherical surface. Well, with me on this class? So if you have like r squared is equal to x squared plus y squared plus z squared, no other coefficients in front of x, y, and z, you get a sphere if you just map that out. That's what it would be. If you take a look with proloid spheroids, when you're in those coordinates, and you use proloid spheroidal coordinate symbols, and one of them is gamma, I think, squared. You get that equals a constant, you get an egg, and that kind of stuff. So they're constant surfaces, but they have all sorts of bizarre shapes, and they are orthogonal. The reason they have these things is to aggravate people. No, the reason they have them is because they help solve differential equations with all these different kind of geometric constraints. That's the reason they're there. Same reason we use x, y, and z, or spherical coordinates. When the problem fits the contours that are out there, you use those coordinates for separation of variables, and the same thing, you use these coordinates for separation of variables. But when you take a look at velocities or anything, say a velocity in proloid spheroidal coordinates, you'll get something that can be vastly different than this, and I'm going to tell you, because if you have a Gaussian distribution for for the proloid spheroidal orthogonal axes, they don't conform to this formula for 3 dimensions. And, it's a lot of information that you don't really see how useful it is, but just be aware of this in the future if you run into these higher order coordinate systems. Okay, all this said, that's going to be the mean squared value. The mean value I'm not worried about, but here's the one thing I want to say. Do you remember when you had the fact that energy itself, we're talking about non-relativistic energy, was 1/2 mv squared. Do you all remember that? That's the energy, kinetic energy of a moving mass in a given reference frame. Well, if you look at this, this is 1/2, and then you can equate it to m, and because that's v squared, you get 3 sigma squared. Now, that effectively, if this is true, then that you can replace v squared there. If you want to talk about the average energy, right, in a molecular movement, you would take the average velocity, and that's the energy of a molecule with mass m. Then, if you go a little bit further, and you replace the actual sigma squared with the thermodynamic constant, which would be kT over m times 3. Now you get 3/2 kT. And this is the one thing I wanted to bring out. T would be temperature in degrees Kelvin. K is Boltzmann's constant. believe it's 6.023 times 10 to the minus 23rd. Y'all remember Boltzmann's constant from, did you have chemistry? Do you remember that in chemistry at all? In thermo? You do remember it, at least somebody. Sometimes I think I'm crazy. It's like, I remember having chemistry. In chemistry and in thermodynamics, they use these constants, they become critical. But that's just the energy in a single molecule of gas. If you want it in a mole of gas or anything like that, you're going to multiply by the number. But that is true, by the way, it's a very small amount. Right? K is 10 to the minus 23rd, think about that. We're talking about almost nothing, but how many molecules in a mole? 10 to the 23rd, roughly. Do y'all remember about that? Something like that? So, without going there, that's what happens. All right, next. Yeah. I want to make sure I bring this up. Next thing, we did the uniform distribution problem last time I brought it out, right? There are two takeaways from it. Anytime you have a uniform distribution, the mean value is just A plus B over 2, and the variance of this, the variance is going to be 1/12. Make that clear. These are the two takeaways. I'm not going to linger on this one. The variance of this is going to be equal to B minus A squared over 12. Now this becomes important. So really, sigma x here is better written as the delta in x, the difference between the upper and lower value squared over 12. Now this will become important right here. The mean value, I think, is fairly obvious. This is the variance. Are you with me on this, class? You can get the mean squared value if you have this and the mean value. You know that the actual mean squared value would be this value plus A plus B over 2 squared. With me? Okay. I wanted to say that. I don't have time to use it today, but I'm going to use that. Finally, the last thing I'm going to do before it's finished, I'd like to do a few others, but it's the exponential distribution. Now this is real important. I'm trying to cut through and do just the distributions we need out of this chapter. The exponential is something we need because it's useful everywhere. He does the proof of this, but if you can say that the likelihood of failure of an event at any point in time to any point in time plus delta t is a constant. You with me on this, class? So that means the likelihood of failure at any point in time could be 5 minutes from now to 5 minutes from now plus a second. If that's the same as it is from in the beginning right here, from t equals 0 to t plus delta t, you will get this distribution, and I'm not going to do the diffie-q's, I only got a few minutes right now, solution, but you will get a differential equation that results, when you solve it, in this, it's called the exponential distribution. It says that f of, and he uses tau, and that just is time, is equal to 1 over tau r times exp to the minus tau over tau bar. You can use any symbol here you want, but it's in time. Here's the important part. What this is really saying is it doesn't matter where it starts and where it stops. If this is time, and we say here there's a failure, or the event happens. Right here. Then if we look at this, the density function, f of tau, at this point we'll have a value of 1 over tau bar. And that's the mean time to failure. I better put this down. Tau bar is the mean time to failure. And it will keep going down, 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 until there's another failure. Now, that's the mean time, so it's probabilistic. Once there's a failure here, it'll go back up and keep coming down, and may go way down until there's another failure. So the only thing that matters about this density function is when the last event occurred. From that point on, you start measuring time. You with me, class? Now, here's what happens. That means the probability of a failure happening, and I guess I can use F of tau. And I'm going to assume it starts at tau equals 0. Here, it's going to be 1 minus exp to the minus t over tau bar. Now, it's not saying anything really, phenomenally interesting, but it's saying this is the probability of the event occurring from the last event to the point t, which is measured beyond the time the last event happened. With me, class? And if you look at this, as t goes to infinity, the probability of an event happening is 1. It's going to happen. Usually it's talking about failures. Okay? Last thing. So the best way to see this is an example. And we're going to say, you know what a traveling wave tube is? You know what a vacuum tube is, right? All right. Well, traveling wave tubes, probably about 20 years ago, they were used a lot in microwave amplifiers to create microwaves and stuff like this. But they have a mean time to failure. In his book, he says, we're going to use a traveling wave tube, and it has a mean time to failure of 4 years. This one's simple, 4 years. It says, what is the probability that failure doesn't happen for 4 years? So just think about this. The probability of a failure happening, right, between 0 and 4 years is given by this, right? What is the probability of a failure not happening then? So it have to happen after that.
1 minus.
It will just be, 1 minus this, or exp to the minus t over tau. Do you all see this? So the probability of a failure not happening or happening later than 4 years is just going to be equal to, and I'll just say fail greater than 4 years is going to be simply exp to the minus 4 over 4, or simply e to the minus 1. That's it. That's how easy it is. And what's the probability that fails in the first year between 0 and 1? Take a look. Wouldn't it be just 1 minus e to the minus 1/4 is the mean? And that's like 0.223 or something like that. Y'all with me in this class? So this isn't a hard one to see. This is for a single event. What we'll talk about next time, just briefly, is called the Erlang distribution. And that's saying if you have this exponential distribution, time to the next failure, what's the probability of 3 failures happening in 5 years? And that's where it becomes something called the Erlang distribution. I'll have to talk about that later. All right, you want your quizzes? Can you do me a favor? Populate this row. Get out of this row and that row. Populate, well, you guys are all over. How about this row? Why don't you move there and you stay, you guys in the last row stay there. And take your phones out, put them flat on the desk next to you.